Okay, let's get started. So today and the rest of this week, we're going to be talking about visualization. For today specifically, we're just going to do an introduction to the ggplot2 package, talk about sort of the basic syntax and construction there. On Thursday, what we're going to do is talk a little bit more about sort of the overarching principles and design process for creating a visualization, as well as some of the larger ggplot ecosystem. So what can you then do on top of the stuff that we've already seen? So today is going to be fairly just run through a bunch of stuff that we'll see, like the basic kind of thing, similar to what we did with dplyr of here are the basic verbs, here's the basic construction. But part of this is going to be around sort of thinking about it in the context of what do I want to generate at the end? Do I want a scatter plot? Do I want a bar plot? Do I want a histogram? That kind of thing. And what you'll hopefully notice is that sort of, again, the common shared features of all of this. It's not about memorizing everything. It's about knowing sort of, okay, here are the basic building blocks. How do I get to the final product that I want? And then how do I change things? So that's the goal. Currently, my plan is, and this is, I will finalize it by the end of the week. There will be one more group assignment that will just be a week long. I normally don't do that, but I think just with the timing of fall break and everything else, this makes the most sense. That will be a visualization assignment. So what we're going to do is give you a data set and a bad visualization and ask you to redesign it. So that will just be a short, fairly contained assignment that will go out end of this week, do the following Friday, and then the next week is when the individual assignment will go out, which will be sort of summative across all of these things. So what you can sort of expect is something that looks an awful lot like homework 2, but with the visualization component added on top of it. So for that, you'll have at least a week to complete it, and we'll work around the fall break and the time off and that kind of thing, so that there's plenty of opportunity to get support and that kind of thing. But that just, the fall break, given we lose the Monday with the labs, makes things a little bit complicated. So that's the current plan. I will update you on Thursday and let you all know what the plan is as it goes forward. But that's what my current thought is. Okay, so ggplot. So this is another package that's part of the tidyverse. It's probably, of all the packages in the tidyverse, the oldest one. It predates a lot of the other things, and it's got some quirks because of that. But what you can see is that it does, in fact, embody a lot of the principles that we've seen there. ggplot2, the name comes from the grammar of graphics. So this is an idea that was published by Leland Wilkinson in 1999. And it's the idea of, let's look at a common plot that we might make, a quantitative visualization of data, and let's think about the constituent components of that. So things like the axes, the things that go inside the plot. Do I use a bar to represent things? Do I use points to represent things? Do I use a line to represent things? That kind of thing. So it's trying to take that sort of overall process, break it down into its constituent parts, and then generate a grammar around that. And we've seen something that's very much inspired with that with dplyr, which is sort of portrayed as a grammar of data manipulation. So we have a collection of verbs that allow us to manipulate a data frame of data to do the sort of common tasks we want. The grammar of graphics is a similar kind of way of describing a statistical visualization and the components that go into it in a concise way, so that we can then build up these more complicated things from some sort of simpler tools. ggplot2 was written by Hadley Wickham, 2009, so this is back when he was a graduate student, before he was at Rice and then at RStudio. So again, it predates almost everything else we've seen in the tidyverse so far, and that's going to show up in a couple places. But the design principles are there, so it has a very compact, consistent syntax to describe statistical graphics. The only problem is it's not going to be quite in line with what we've seen in terms of the consistency of the rest of the tidyverse, particularly on pipes and that kind of thing. It's very modular, so again, it's about building the more complicated thing by composing simpler elements together. And as we go through right now, ggplot2 is not meant to tell you how to make a good or a bad plot. It gives you the tools to build a plot. Whether that plot is good or bad depends on your use case and what you're trying to do. It's very easy to make bad mistakes with ggplot. It's very easy to make good plots with ggplot. I will say, compared to BaseR, it's much easier to get sort of production quality plots out of it quicker than it is with BaseR. BaseR, you get a little bit more control over all of the bells and whistles, which is great. But you spend a lot more time fiddling with the details versus something like ggplot. It's sort of a little bit more consistent and nice as you go. And what I will also say is, actually, in this day and age now, if you get used to sort of noticing some of the properties of ggplots, you actually start seeing it all over the place. They show up in the New York Times all the time, Financial Times, all sorts of places. So it's a very common tool that's used widely for a variety of things. So ggplot2 is also opinionated. There are certain things it will let you do, certain things it will say, that's a bad idea, you shouldn't do it. But we'll sort of go through examples of those as we progress to sort of talk about them. So it tries to steer you in the right direction, but again, nothing replaces good design sense, trying to solve a problem with it, which is what we're going to talk about on Thursday. Okay, so to delve into sort of the grammar of graphics and the common terms that we're going to use, we are attempting to create a plot, a statistical graphic, whatever you want to call it. And so any statistical graphic is going to be the following thing: a mapping of data. And so what we mean here is a data frame or something like that, so a representation of measured quantities. We are then going to do things like potentially transform that data. So that could be through summarization, so taking a mean or a standard deviation or a median, log transforming it. All of these kinds of things are common things, even potentially summarizing it by fitting a statistical model to it, but some kind of transformation of that data, or just the identity not doing anything at all. Those resulting transformation things or untransformed data are then mapped to these aesthetic attributes. So these are properties that are in the plot itself that then represent those quantitative bits of information. So things like the color, the size, the position on the plot, so on and so forth. There are lots and lots of aesthetics we can play with. Not all aesthetics are created equal. So again, remember, at some level, the goal of a statistical graphic is to convey quantitative information. Our brains are better at recovering certain kinds of quantitative information codings than others. So our brains are pretty good about position. They're a fair bit worse about judging area and size of something. And then they're even worse about judging color of things in terms of like trying to recover exact quantitative measures of things. People actually do psychological studies on these kinds of things, showing people a plot with a different representation and say, okay, that point there, what number does that represent? And people try to do that and see how well they actually do. So these are measured things. Once we have those mappings get applied to some kind of geometric representation. And so this is things like points, bars, lines, whatever the kind of plot that we're trying to create, what's going to then be physically represented on the screen. And then what we may do is an additional set of mapping into a sort of faceting system. So if we want to break the plot into small multiples, we'll see what that looks like. Or if I'm using an alternative coordinate system. So if I'm doing polar plots versus XY or a log scale or something like that, that's this final sort of last transformation before we actually represent it to a user. So again, the things in bold are bolded there because these are terms that are going to come up over and over again when we're talking about the properties of ggplot and the arguments to the functions and that kind of things. So our data, transformations, aesthetics, geoms, facets, and coordinate systems. Okay, ggplot calls should look fairly familiar to us. They always start, for our purposes, with a call to the ggplot function. There's going to be some setup there where we define the data. That's going to be mapped to a data frame. The mapping is then going to be set up by a call to this AES, this aesthetic function, that specifies which variable in the data frame are going to map to the various aesthetics. And there might be 1 or 5 or however many we want. Once we've done that, ggplot uses not the regular pipe operator, the Magritte pipe we've seen, it uses addition. And again, this is because ggplot was written before Magritte existed. So it's an alternative implementation of the pipe that is specific just to ggplot. So it's overriding the addition operator in R via S3. And so what we do to chain ggplot commands is just to do addition to the next thing, to the next thing, to the next thing. I can guarantee you at some point you'll put a regular pipe in there. They've done a lot to make it clear that that's an error, and it will give you an error saying that did you mean to use plus? You shouldn't be piping between ggplot objects, that kind of thing. Doesn't always catch it, but the vast majority of the time you'll see something like it. But it's a super easy mistake to make. It is something that they do intend to fix at some point, but it's basically involves rewriting the entire package at this point. So it's not something that will happen anytime soon. So then we have these geometries. All of the geometries in ggplot are geom as a prefix, and then the name of the geometry, and we'll talk about various examples of that. Those geometries can have additional sort of aesthetical mappings, that kind of stuff. That's particular to just that geometry versus everything else. We can then apply other kinds of manipulations to it, so scaling, so changing the scaling of our axes, changing our coordinate system, faceting, so on and so forth. But the whole point of this is it looks very similar to a dplyr chain where we just take one thing and then we just keep adding to it and layer it on as we go to change the behavior of stuff. So the data set we'll look at, I think I've showed you this before. This is the Palmer Penguins data set. It's a nice one to show you because it's a data set that involves both numeric and categorical variables. So we get a variety of both kinds. It's big enough to not be like trivial, but not so complicated that we can't sort of look at it easily and play with it. So these are measurements on 3 different species of penguins in Antarctica at a research station on the Palmer Archipelago. So there's a bunch of different islands with these different species occurring on them. These are physical measurements of these 3 different species, so things about their bill size and their flipper size, so on and so forth, their sex, the year these things were measured, body mass, that kind of thing. So what we'll start with is a sort of full ggplot pipeline. Then we'll start pulling about all these pieces and talk about how it works in more detail. So this is a basic ggplot. So we've got all of those components we were just talking about, putting it together. And then on the right-hand side is the result of that. So we've got a title, we've got axis labels, and in this case, what we've generated is a scatter plot of 2 numeric variables. So at some level, unlike sort of the plot function in R, if you give it certain kinds of data, it will decide, oh, we should represent this with a box plot, or I should do it this other way, or a table, or a histogram. Versus ggplot, you need to be very explicit. So what makes sense to represent 2 numeric variables is a scatter plot, but I need to be explicit about that and tell it to do that by picking the appropriate geometry in this case. So there are additional knobs that you need to turn to make sure you're doing the right thing as you go. So let's go through sort of the individual elements of this and talk about each of the components and how it puts together, and like also what this would be represented as in terms of text as opposed to code. So we are going to start with the Penguins data frame. And so the kind of cool thing here is it doesn't show up very well, but even this is a valid call to ggplot. I just haven't told it how to do anything. So all that it does is it just draws a gray square. Like there's no axes, there's nothing else because there's nothing for it to do, but I still get a plot out. And so for this kind of thing, for demonstration purposes, it's really great because I can just show you one change at a time and what changes in the plot as we go. And again, behind the scenes, all this magic is happening because of S3, and ggplot overwrites the S3 print method. So if you return it, it tries to print it out, it creates the plot in your viewer in RStudio. So first we start with Penguins data frame. Next, what we're going to do is we're going to map bill depth to the x-axis. So second argument in ggplot is the mapping, which is the call to the aesthetic function, with then named arguments being the name is the aesthetic, the value is going to be the column from the data frame that I want to use. And note this works just like dplyr. It's doing sort of that non-standard evaluation thing, so I don't have to quote it or I don't have to do Penguins $bill depth to figure out which one that should be. So it's pulling that out automatically and figuring out that should be the case. So in going from this to that, the only thing that changed is I've now given it something about the x-axis, so it has in fact drawn an x-axis for me. So I'm getting values there. It's picking reasonable tick marks, that kind of thing. Now we want to map bill length to the y-axis, so do that. I get now something that has a y-axis. This behavior with the gray background with the light gray rules on it is just the default theme for ggplot. That's something that you can change if you wanted a different color scheme or something else like that. Okay, so we now have an x and a y-axis, but we don't have anything shown there until we tell it how to represent the data with a particular geometry. So in this case, geom_point. For each data point, I now get a dot on the overall plot. I want to now separate the points by the species color. Or sorry, I want to map color to the species so I can tell which species is which. So I do that here by now. I'm applying this aesthetic color is equal to species. I'm doing that in the context of geom_point because I want that color to only apply for that particular geometry. So that, by doing it here versus in the ggplot, determines sort of the scope of where that mapping occurs. What we can see here is, at least nice for us, that these 3 species are somewhat different from each other in terms of these measurements. We have sort of 3 distinct clusters for each of them that are separated. I can now change the other sort of important things, things like the title. So this is via the labs function. So I'm setting title is equal to bill depth and length. I can add a subtitle. and I can rewrite the x and the y labels in a nicer format as opposed to just using the variable name. And similarly, I can change the name on the legend. So before it was lowercase species, because that's the name of the column, but maybe I want it capitalized, so I can just replace that. So note, labs is letting me manipulate any of the labels on the thing, but in a sort of convenient way. So I can manipulate a scale, I can manipulate a aesthetic, and I can manipulate the overall title of the plot. And if I wanted a caption to say this is where it came from, I've done that. So source Palmer's Penguins package. Not a very good citation, but it works. And again, all of these things about the positioning of where the title occurs, how big the title is, where the subtitle occurs, where the caption occurs, all of those are also further adjustable. They're controlled by the theme, which is sort of a bigger sort of meta concept about the plot, but you can move those anywhere you want if you're so inclined. If we want to change the color pattern or the color palette, in this case, I can swap over. So Viridis is another color palette option. In this case, so one of the problems with sort of the default one is for human visual perception, different colors don't have the same visual salience. Our eyes are drawn to certain colors more than others. So in this case, the default one is not terrible, but there are certain color palettes that are designed to be sort of more sort of evenly perceived by our vision. And so Viridis is an example of that. It's not so useful in this case for things like scatter plots, but for things like a raster plot or a spatial plot of some kind mapping, Viridis is very commonly used because it doesn't tend to have that problem of noticing certain areas over others. But note, we get a different color palette. It's also automatically updating my legend, and everything else sort of comes along with this automatically, which is really nice. If you've ever dealt with base R and the legends function, it works, but you have to do all of that bookkeeping yourself to make sure that the palette colors match the colors of your plots, everything is in the right order, everything like that. It's super easy to make a mistake. So in particular, a lot of the power comes with ggplot is particularly around this multivariate visualization. It's really easy to add additional variables to your plots to get much more complicated things quickly. Like a very simple x versus y scatter plot, nothing is going to beat base R plot because it's super quick and it's easy. But as you want to add more and more variables, the bookkeeping gets heavier and heavier for base R versus ggplot. It's just very straightforward to add these things on. Add another aesthetic, you've got another dimension, so on and so forth. Okay. So again, this just gives you some idea about building it up. And again, the nice thing here is that you can see the progress as we go. So as we add each individual line to this, we see the progression of the overall plot. Generally, what I've done here has been very explicit about all of the arguments and naming them. It gets really boring typing data and mapping all the time. So very often we leave that out. In most ggplot code you'll see in the wild will look like that. And the thing to just keep clear in your head there is that the order of the arguments does swap between the ggplot2 function versus the geoms. So geoms take an aesthetical mapping first versus ggplot2 takes the data first. This makes sense if you think about it because for ggplot2 we need to start with data. That's the most important thing. Most of the time with a geom you're just referring to the existing data set that you're already using. But there are some cases where you might want to add an additional data set on top, so you can provide that specifically to a geom via the data argument, but that's not something you commonly do, so that's why that argument gets moved somewhere else. So that's the only point I'm trying to make here. So again, just note that this is the first argument here versus the second argument there. Okay. ggplot aesthetics. There are a bunch of them. Generally, the best way to look at this is to look at a particular geom and look at the help file for it. Once you do, at the very top of each of those help files, it will list this particular geometry pays attention to the following aesthetics. These are the things that you can set. Most of them are fairly straightforward, but if you're trying to do things like area plots or ribbon plots or something else like that, they have some things that are specific to them in terms of like the Y max, Y min, like the range that you're filling in, that kind of thing. So it's good to pay attention to all of them, but again, the bread and butter are going to be things like X, Y, color, shape, size, alpha, which refers to the transparency of it, of a point or a plot element. Those are going to be by far the ones you see the most often, that most of the geoms use if it makes sense in some way. So again, if you go to the help files, I'll pull this up really quickly. So these are literally the help files that are in ggplot2. The nice thing is, though, if you go to the Tidyverse website, and so this is a package down site, the nice thing about that is it goes to the help file and it runs all of the examples and shows you the output. So you don't have to do it yourself. So this is the main sort of high-level reference for everything. If we go to, say, let's look at geom box plot. Here's the list of the aesthetics that it uses. And then if we scroll down further, we see various examples. And so again, if you just use the help function in R, you'll see these examples. You just won't see the output there. You can run them yourself. So see just variations of ggplot2 box plots. And we'll go through these in a little bit of the various orientations and options and so on and so forth. So the documentation is fantastic for that package. Do make use of that. And as I've mentioned before, we can set up aesthetics globally. So any aesthetics that are set in the ggplot call, those apply universally across all the subsequent geoms. Or we can do geom level specific aesthetics, again, with that call within that particular geometry. Those will then override the global ones. Again, think about like variable scope, that kind of thing. So if X is defined in the ggplot, but I define an X aesthetic in my geom, the one in the geom will be one that takes precedence. So we can override things, you can do whatever you want, but it has a sort of a natural inheritance structure, so it makes some kind of sense. And generally, things like defining your X and your Y axis are going to be consistent across all of the data and everything you want, so you set that up in the ggplot so you don't have to repeat yourself. Okay, so we'll just go through a quick tour of some of these aesthetics and what they do. So we've already seen color applies the color of whatever the thing that you're printing out. So in this case, for a point, it's just the color of the point. Shape is the sort of, again, think in the context of a scatter plot, it's the plotting character you use. So PCH in base plots. Again, in this case, ggplot picks default shapes for you that are reasonable most of the time. So if you look closely, they're a little bit tiny here. It's going to be a circle, a triangle, and a square for the different species of penguin across these. The thing to note here is at this size, the color is really salient to you, right? You can see which penguin is which species, but the islands are really hard to tell apart currently. We can also double up, so I can apply both color and island to the same variable. That's fine. We now have different shapes and colors for each of the species. The nice thing here that happens is that that gets collapsed in the legend into one thing. So now that species entry is showing me everything about that particular setup. So I see that the Adelie are the red circle of the red diamond, whatever it is. Chin traps are the green triangle, so on and so forth. So again, this is the power of that sort of naturally, automatically built for you legend that takes into account all of this kind of stuff. And however many additional sort of aesthetics you map there, same thing will happen. So if we had a line, we would see the line in that as well. Okay, so what we saw is that size matters. Like we couldn't tell these things apart. So if I'm trying to use something like the shape attribute to say something, then I might need to make it bigger so that this becomes visible. In this case, what I've done, though, is I've made size to a fixed value. So I'm setting size is equal to 3. Note that that is not within the aesthetic call. It's outside of that in the overall geom call. So this is the difference between a mapping versus a setting. So mappings go in the aesthetic, and they're related to the data, versus a setting is something that's sort of universally set for all of the values within that geometry in this way. So in this case, I want everything just to be larger, so I set size is equal to 3. That universally applies across all the points, regardless of what the data was. So that's why it goes outside of the aesthetic and is set in that way. Note also, it's a little bit subtle, that size change is also reflected in the legend. So it's also bigger. All of those properties are getting mapped there as it comes together. You can map size to the data. So in this case, I'm mapping it to body mass, and we do get a legend for this on the right-hand side. But note, these different sizes are fairly hard to tell quantitatively apart. You can tell this one is bigger than that one, but not much beyond that. And you can look at the scale there. You could adjust that if you wanted to, but it's mapping something about sort of the overall sort of put a square around each of those plot characters, how big it is. Note that this also clashes somewhat with the different kind of plotting character shapes we're using, because triangles are hard to judge against squares now. Like, am I looking at the area of the thing or the overall size? They're not sort of easy to do apples to apples comparisons. Alpha is another common one, and this is particularly very useful for plots with lots and lots of data. It changes the transparency of the points. So basically it makes them semi-translucent. It's a scale between 0 and 1 usually. Or if you give it a mapping to the data, the max is 1, the minimum is 0, and it goes in that range. Or maybe not quite to 0, so not everything's completely translucent. But this is very helpful in the case of lots of data because there's a problem of overplotting. All the points are right on top of each other, so you can't tell, are there 10 points there or 1,000,000 points there? It looks exactly the same. Versus if you crank up the alpha, you can start to see where the density is, where there's more points versus less points, that kind of thing. Here in this case, I'm mapping it to a variable. I don't think that's super useful. We're not very good at judging how transparent something is. Again, we can tell this is more transparent than that, but not by how much. So it's not a very good quantitative aesthetic. But it is more useful sort of often as a setting to make everything a bit translucent so we can see where the overplotting is. OK, so this is just what I was saying about this mapping versus setting dichotomy. Mappings are this mapping of the data to an aesthetic. A setting is just a fixed value that we're applying to an aesthetic in some way. They can both be used, so anything that can be an aesthetic can be either set with a sort of fixed value or mapped to the data. It's up to you in terms of how you do that, but it's just done in different ways. So using the aesthetic and the mappings argument, or just directly applying a value to that attribute in the context of whatever geometry you happen to be using. OK. Any questions so far? OK, the next sort of useful common thing that we do as a way of representing data is this idea of faceting or small multiples. So what we often can do instead of showing one big plot with lots and lots of attributes is to take that plot and split it into a bunch of smaller plots that focus on one particular characteristic. And in so doing, we'll often see patterns that are not visible in the single sort of monolithic plot. And I'll show you some examples of that in just a second. But this is a very, very powerful technique to showing more data, more variables, more dimensions in your plot, while still keeping it readable and still understandable. But again, how you do this depends very much on what you want to accomplish at the end. And again, we'll talk about that in some detail on Thursday. So these are done via the faceting functions in ggplot. So the first one is facet grid. So in this case, what you do is you provide which variable maps to the rows and which variable maps to the columns. So in this case, what we can see is that I've got a formula interface to do that. I'm using something tilde something. Think about this like LM in a linear model. So I've got y tilde x. The thing in the beginning will be the rows. The thing afterwards will be the columns. So species go in the rows. Islands go in the columns. And so since there's 3 of each, I end up with 9 small plots. So what's super evident in this plot that maybe wasn't evident earlier? Yeah.
There's gaps in our data.
Either there's gaps in our data or these species don't occur on those islands. Yeah.
There are species that don't have.
Yeah. So in this case, what we're seeing is that these Adelie penguins occur across all 3 islands, but the chinstraps and the gentoos are confined to only one island. And that may be a quirk of the sampling scheme, that one year they went out and collected just the Adelies, and the other year they only went out to one island and collected the chinstraps. Or it could just be that this is a biologically relevant thing, and they only occur, or they only have rookeries on certain islands. We don't have enough context here to say definitively what it is, but the point is this plot makes it super, super clear that that's the case. If we compare it to our previous thing, where this is the same information, right? I'm using the species and the island to represent things, but it's a lot harder to see the fact that some of these species don't occur on all the islands. Your brain is just not good at picking that out from this information. And again, that's partly about the shape, but more about it's just everything's on top of each other, so it's not super easy. I will say versus this, it's a little bit hard to tell here that these species are clustered. Like, it's clear we can tell about this sort of single island species. Yes, they're a cluster because they're all together. But it's a little bit harder, at least it takes a little bit more sort of thought process to see, okay, this and this and this are all right on top of each other, so that conforms to a cluster itself. That's harder to judge here versus in this case, okay, we can see, in fact, that the adeles are all together in that bottom right quadrant, and that's separate from the other ones. So again, what this comes down to is what task, what are you trying to show somebody who's looking at this visualization? What are they trying to get out of it? If I'm trying to tell a story about these species are distinct from each other in terms of their physical characteristics, this is a better plot. If I'm trying to show that these species are different in terms of living on different islands, this is the better plot. So it really comes down to what I want to do, what story do I want to tell when I'm constructing something like this. With facet grids, we can also do this in a way where if I just wanted to do a single variable, I can. So it turns out it's just a little bit awkward with the formula interface. Tilde species is perfectly valid R syntax, so that's okay. If I just want columns with my small multiples, great, that works. If I want to do it the other way around, where I want to populate the rows with them, the issue is the formula interface in R with the tilde has to have something on the right-hand side. It doesn't have to have something on the left-hand side. So in this case, we're using our favorite placeholder, which is just dot. It doesn't mean anything. It doesn't get used anywhere. It just says this generates a valid R expression that can then be evaluated by ggplot. If you left that dot off, it would give you an error saying the formula is invalid. So again, it's slightly awkward, slightly old school way of doing this kind of things, but it's a sort of a clever hack of this flexible tool in R with the tilde. If you played around with case when with dplyr, same thing. There's a bunch of hacks similar to the per style anonymous functions are all hacks of this formula interface because it happens to be very, very flexible, and you can do a lot of things with it. One other option is facet wraps. So if the thing that you're trying to facet has a lot of levels, so very often this is done with a categorical variable, what we might want to do is just show those. So in this case, it's going to populate them into the columns, but it will do so with a limited number of columns. You can specify that. So 3 is not too bad. I don't have a high level factor here. But what I can do is I can say, okay, to conserve space, I can set the number of columns to 2, and the wrap here clearly just wraps it around, and it'll still fill it out. So if I had a factor that had 9 levels, facet grid becomes a good option so that I can get a 3 by 3 as opposed to a 1 by 9 kind of layout. The other thing to note here that's nice about these is they are often much more compact than doing something like par mf row with base R, because by default they share axes. So this shares an axis with that, so we only need to show it once on the left-hand side. Similarly, like we go back here, we see that there's just the y-axis here, just the x-axis here. We're not sort of duplicating those, taking up extra space. So you can do that with base R, but again, the bookkeeping is kind of a headache to make sure that everything maps out. You don't have to do that. You can set the scales to be free on the x, free on the y, so that they'll be different if you need to. But the default behavior is to assume that the x and the y-axes are shared, so we can collapse that. And all of this works then with other aesthetical mappings. So if I wanted to just show colors as well as the facets, totally fine. In this case, the legend is a little bit redundant because that information is already conveyed by the plot that it's in. I can see by the row. So you can also turn all of these things off. So guides, that's the reference to the elements of the legend. I can just set color equal to false. So now it's just not going to show that legend element. And it goes away. Now stretches out nicely to fill in that space. So again, all of this stuff is infinitely customizable to turn on and off for whatever you're trying to do, which is great. Okay. Next little bit is just going to be very rapid fire. Let's just go through different plotting things that we can do, what happens with the basic aesthetics, that kind of thing. It's not remotely in depth in terms of the more complicated things you can do with ggplot, but just to give you some idea of the most common type of plots that you might want to make. How do I do that in ggplot? What does it look like? Okay. The Swiss Army knife of statistical visualizations. So if I'm trying to look at a one-dimensional visualization of numeric data, bread and butter for that is going to be something like a histogram. So in this case, geom histogram, fairly straightforward. Here I just mapped my one numeric variable to x. And so in this case, what it's doing is doing that calculation for me. So it's binning things based on, in this case, a default of having 30 bins, which may be good, may not be, but it's something that I can control. And so it creates the bin sizes, counts them up, does all of that calculation for me. In this case, it is going to whine at me a little bit saying, using bins equal to 30, pick a better value for bin width. That's a good idea, right? Because your histogram can tell a different story depending on how big your data is, like how many observations, and how big your bins are. You have too few bins, it may look smoother than it is. You have too many, you might see it looking like more jaggy than it actually is real. Where those cutoffs are matter. It's arbitrary in some sense. So that is adjustable. So I can set the number of bins to have sort of a total number of bins. I can also set how wide I want the bins to be in terms of the units of x. So 250 units wide, whatever you want, you can control that. And note, when I do that, it doesn't complain at me anymore, telling me that I should set something more reasonable than 30. 30 is not a bad number, it's just probably not the best number for your data. You should probably pick something else. We can also facet these things and color them. So again, think about this as being a group by and then summarize in dplyr. So what I've done here is I've now applied a grouping variable with color that's sort of separating the species. So I want to see how does this variable differ in distribution across the three species. Geom histogram with bins. Note here, color doesn't look great on a histogram because color refers to the outline of an object, not its interior. Again, it's just a default construction here. So I get black interiors with the colored outlines. That doesn't look like much. The better option here is fill. So the two options that control color of things is fill or color. If one doesn't work, try the other one, and you're probably going to be fine. But again, generally, it's going to be things that use rectangles of some sort. So histograms, box plots, bar plots, that kind of thing, where fill becomes necessary. That's great. I can now compare the three different species across this. But note, what happens is it draws the adeles first, and then it draws the chin straps, and then it draws the Gentoo on top. So I can't actually tell what's going on over here for the adeles or the chin straps penguins, right? I've hidden that part of the, I know it's less than the Gentoo, but I don't know by how much. So in this case, where we now have, again, this is a small case, but this is overplotting, or I'm missing things, that's where we're doing something like this. So changing the alpha values changes that so they're now transparent, and I can see where they overlap, so I can see where each of these curves go. Note that it does make it a little bit harder because I need to know that the purple is the blue and the red together, and the darker blue is the green and the red and the blue together, so on and so forth. But you can see where these different areas are and get a better sense of the three distributions as opposed to all of them together. I don't remember what that does in this context. I'm not sure if it's even necessary. Let's try it. So you get ggplot if you load tidyverse. It's one of the base packages there. And then the penguins are in the Palmer's Penguins dataset, our package. So we run that, we're getting the same plot we just had. And now let me take the identity out and see what happens. So this versus that. Oh, yeah, you're absolutely right. So in that case, what's happening is it's not showing them on top of each other, but sort of the cumulative distribution with the contributions by each of the individual penguins. The other way of avoiding this is just by faceting. So now they're not on top of each other. I can compare them. This is better for comparing things like the range, so the min and the max, where the mode is, that kind of thing. But it becomes harder to do sort of absolute comparisons of like which one's taller. That's still possible, but you have to sort of look and see, okay, this one's at 15, and then go compare to the other one, so on and so forth. Again, it's about trade-offs in terms of what you want the user to use or get out of a particular plot as they go through. And so again, note I've turned off the guide here because the species is already sort of implicit because of the faceting. It's already labeled on there, so I don't need the redundant information. Next option are density plots. So this is just a basic kernel density estimation of that data. So again, it's a way of sort of getting something that looks a bit more like a continuous distribution as opposed to something that's a bit more spiky, like a histogram. Again, you can change the behavior here around like the bandwidth that it uses and other stuff if you want, but it picks one that's very similar to what base R uses with the density function. It picks a reasonable size based on the amount of data you have. So again, gives us an estimate of what that distribution looks like. We can color them in. So again, we're doing that with fill as opposed to color, so we get the interior as opposed to the exterior. And if we split it across the species, now we still have that overplotting issue. So in this case, we get a clear view of what these three things are. And so what it seems to be saying is, like, in terms of this, clearly the Gen 2 penguins are much bigger versus the Delhi and the chin straps are about the same size based on the body mass. And adjust here is that bandwidth. So how wide should it be? So in this particular case, it's between 0 and 1. So like the bandwidth to include all of the data for each point or half the data or something else like that. So you can tune it. So I've tweaked it down here. In this case, that means I'm using a narrower bandwidth. So it's going to be jaggedier, spikier as I go across. So it's up to you to decide what the appropriate one is, just like the size of the bins for a histogram, to decide what's real versus what's an artifact of the sample that I have. So this is probably overly spiky for my needs here. I'd want something that has a bit wider bandwidth. This might be overly smooth on the other side. Violin plots. So these are just density plots turned on their side, reflected. I'm not sure that they're super compelling is better or worse, but again, it's something that's just built in. So if this is what you like or what your collaborator wants, super easy to generate. And again, they're nice because they're sort of side by side. They do give you more information than what you get with just a box plot, say. There are other packages. So I don't think ggplot does half violin plots, which is just essentially density plots, but separated. But there are other packages that do implement that. And so the tidyBase package I was using for generating the data from the first homework has a bunch of built-in geoms for ggplot that let you do the common kind of plots that you might want to make for a Bayesian analysis. So caterpillar plots, half violin plots, that kind of thing. Another one that's useful, this is a ridge plot. They are also sometimes referred to as joy plots because there's a famous album from Joy Division with one of these things from some astronomy work back in the 70s or 80s, which is kind of cool. But what it is it's just a bunch of density plots where we're separating them on an axis, but we allow them to overlap so we can put them more closely together, because often what we're doing is comparing over time or wavelengths or something like that, so the points are related so we can see some comparison. But again, this makes it a little bit easier to compare things like the peaks of like how do they change from one to the other as we go through. So in this case, that's not something that's coming from base R. It's coming from an additional package. Sorry, it's not coming from base ggplot. It's coming from the ggridges package, which adds this geometry so that I can then do this other thing. So ggplot in particular has this really rich additional ecosystem of other tools that people added on to add new geometries, new scales, new color palettes, that kind of thing, new themes to do all sorts of interesting stuff. So in this case, doing it with more categorical variables. So here I'm now combining some data munging with the plot. So what I'm trying to do here is combine both the species with the sex of the penguin to see if they're sexually dimorphic or something like that. So I'm creating a new column called species sex, which I'm just pasting these things together. But that's enough to create a categorical variable that now has 6 levels. So one for each penguin species times the 2 sexes. So that's giving us a comparison. And then I can now do my ridge plot with X and Y, and then coloring by species, so I get something that I can now compare the males and the females to each other, and in this case, certain ones of the Adels and the Gen 2, the data wasn't recorded, so we don't know. So those show up as NAs as a separate option there as well. But you can start to see how this gives you, particularly a ridge plot, gives you more compact representation of these things as opposed to stretching them out, making things a little bit easier to compare across the board. Box plots, not something super useful in the real world, but if you TA Stat 101 or Stat 199, you'll see a lot of them. So it's useful to know how to make them. So again, they're just sort of a representation like the 5-number summary. It's a really bad way of calculating outliers, but it is what it is. They come up a lot. You have lots of options to play with them. So note that I can normally, we represent these with the numeric variable on the x-axis, the categorical variable on the y-axis. It used to be once upon a time in ggplot you had to do it this way. And if you wanted it the other way around, you'd have to do coordinate flip. More recent versions of ggplot doesn't care. Whatever you want to put into the x and to the y, it's fine. It will then just pick out the appropriate thing in terms of what goes where, which is the categorical variable, which is the numeric variable for separating things. Scatter plots we've already seen. Something cool that you can do with scatter plots and other sort of numeric data is we can include best fit lines. So this is geom smooth. In this case, geom smooth by default, again, it depends a little bit on the amount of data you have, but typically it will use this low-S model. So this is a local smoothing model, local linear regression. So what you get is something that is sort of natively wiggly, will fit the data in a way, but not follow every sort of variation up and down as it goes through. And it will tell you what it's doing. So in this case, it's saying geom smooth is using low s with the formula y tilde x to fit. And so low s is a built-in function in base R for fitting this kind of model. What we get is then that model fit. It's going to take into account all of the aesthetics we're using and all of that grouping that sort of implies. So what this means is I get 3 separate models, one for each of the species as I go through. And I then get some idea of the uncertainty. So in this case, I believe, and I'd have to double check, that gray area is plus or minus 1 standard error from the model. So a prediction interval, not a confidence interval. Or am I getting? Sorry, a confidence interval, not a prediction interval. So about the model, not about individual point observation predictions. If instead we wanted to use a different model, you can do that. And so there's a bunch of these things that are built in with method equal to. So here what I'm doing is just fitting a simple linear model. So LM gets used to fit there. I'm turning off the uncertainty, so I don't want to see the error bars. I set S equal false. And full range now does the prediction across the entire range of the x-axis as opposed to just the range of the data for that particular subset of things. So the usual caution of don't extrapolate beyond your data set. But in some cases, we might want to know sort of how these all compare. It looks a little bit nicer. So in this case now, we're extending those bars across the entire plot as opposed to just where the species are. Line plots are just like scatter plots, but the lines get connected together. Often you need to provide one additional attribute here, aesthetic, the grouping variable, which just tells you that things that have the same value here are going to be connected by lines. The other thing you need to be really careful about with line plots is it does it in the order that the data occurs. So your data needs to occur in the order where the line will go. So very often we use line plots with things like time series, and very often they're already naturally ordered by the time, so that's fine. But if for some reason your data gets scrambled, you'll get something that looks like a bird's nest because it'll go like this back and forth over the point to connect everything. So you need to imply the order that it should be in by ordering the data before it gets there. But otherwise, it's very straightforward to create these things. Just sometimes you need to provide this additional grouping variable on top of the group that you specified via an additional aesthetic like color. It's something where it's a little bit fiddlier when you do that. And the other nice thing is you can start overlaying these things on top of each other. So if I want to emphasize where the actual data was measured, I can draw a line, and then on top of that line, I can draw points to show where they are, and I can change their size to emphasize them or something else. I can show points where there's an imputed data thing. If that was something I was interested in doing. Lots and lots of possibilities. Bar plots, by default, this is not a representation of a number, but it's a representation of a summary of your data. So in this case, X is the species, so the bar plot by default is counting the occurrence of each of those things and then giving me the number of them. You can change that behavior if you want, but it's something that it's not. So if I knew that the bar should be this high, I can do that explicitly, but it's a little bit more complicated. It's designed to be this sort of summary kind of thing. You can also do things like stacked bar plots. So we give it the main variable as x, and then a separate variable to separate by within that, so color, fill, whatever we want. And so now we see sort of the contribution of of each island to each species. So again, this is a plot that now shows very clearly the Adelie penguins occur on 3 islands, the other ones only occur on 1 island each. So that becomes much more explicit there. Position fill, so if I want bar plots to be normalized so they all add up to 1, so the relative proportion of each species on each island, something like that, you can do that. We can also do dodged bar plots, so these are sort of bar plots that are side by side within a second faceting variable. So we can then, in this case, this would be the idea of comparing the number of each species and then the sex that was measured for them. So in this case, this sort of shows across all of these Adelies and Gentus, there's a handful of them that don't have sex data recorded, but otherwise that they're both sort of, again, if we're assuming random sampling, equivalent sex ratios. So equivalent numbers of males and females in the sample. So that might be an artifact of the sampling design, or it may just be that that's the natural sort of representation of that species. Note the one kind of weird thing here is it's not taking into account, so this has 3 categories, this has 2. Because it doesn't see the 3rd category here, it's getting ignored, and then these bars are a little bit wider than these ones. There's probably a fix for that, but I don't know what it is off the top of my head. So probably in this case what you'd want to do is just filter for the NAs beforehand and then create the plot, but that's fine. Okay, so we're a bit early, but I think that's going to give us time to go through these then. So 2 exercises here. So this is just using the Palmer's penguin data. I've created 2 plots. The first one is just a density plot of the body mass faceted by the sex of the species, and then also showing the species, showing a variety of density plots for it. So this should be a bit straightforward. And then this is the plot that shows at the beginning of the repo for the Palmer Penguins package. So it's like the example visualization for the data set. So what I'd like you to do is to try to go through the process of recreating both of these plots from scratch. So they're both just using that penguins data set. That's where you start from. But then start adding the various pieces of this to get to as close as you can that final visualization. So I'll give you about 10 minutes or so to do that, and then we'll take the final 10 minutes to go through this together and talk about that process. And again, certain things like matching the colors here is a little bit more complicated, so if that's the only thing you can't do, totally fine. But try to do as much as you can to get as close as you can as you go through. Okay, let's go through these. So we'll be flipping back and forth regularly, but we're just going to start with penguins, pipe to ggplot, and the first thing I'm going to do is, let me make sure I load the appropriate things so we'll come back to it later. Okay, so in this plot, what are my core aesthetics, our core mappings that I'm worried about? So mass, species. So in this case, we look, the x-axis is the body mass. Since it's a density plot, we do not have a y aesthetic, but we do separate the species based on their color. But in this case, since it's a density, I'm going to use fill because I want the inside of it as opposed to the exterior. So I'm going to set fill equal to species. So if we plot that right now, nothing exciting comes out because we haven't specified a geom yet. So I can do geom density, run that, and just start. Looks somewhat in the neighborhood of what we're looking for. But we also then have this facet grid based on the sex of the penguin. So actually, let me do this. So I said it might be a facet grid, but that's actually not the case. And the way that you can recognize that is because each of these elements has the label at the top here. If I had done grid, it would have applied and put this in the column. It would have put the label on the right-hand side. The reason I would avoid that in this particular context is reading vertical text is harder than reading horizontal text. So putting the label here makes it just a little bit easier to read as I'm going through here as opposed to putting it on the right-hand side where in this case I don't have to do that. So in this case that tells me that this is going to be a facet wrap by sex. But two issues. First, I have too many columns, and the second is I want them stacked on top of each other. So the first one is easy. I can just tell it that I want only a single column. So that's a bit better. But the issue is we also have these NAs sticking around. So the fix for that is not in ggplot. What we can do is just use dplyr earlier on. So I want just not is NA of sex and filter that out. So one of the nice things is all of these pipelines just become something that I can go back earlier, insert a new step, and then run the rest of it, and it should all work. So that's not bad, but we have the overplotting issues we saw before. We can adjust that with alpha, so a value between 0 and 1. So let's try 0.7. That looks a little bit too dark. It's a little bit more faint, so again, just try to pick something that's reasonable. We're not trying to get exact, so that's not too bad. The other issue is our plot has no borders on the density plots. So we've seen that that's controlled by the color attribute. And so what we want here is not any color at all. And so we can actually do that. Is it null or is it NA? Let's try. So if I try null, aesthetics must be either length 1 or the same as the data color. So null has length 0, so that doesn't work. The next best option for getting rid of something is NA, and that did it. So that drops it off. We're pretty close. Those look reasonable. The only thing that's different here is the labels of things. So the body mass is a nicer name, species is a nicer name, and I don't have density on the left-hand side. So we can change that with the labs function. And so x is equal to body mass grams color is equal to species. And, or sorry, it's not color, it's fill. And what I'm going to do is I'm going to set the Y label to just blank. So I just don't want it to show density at all. And that works pretty well. Okay, so that's the main part of it. So what I want to demonstrate really quick, and this is going off script, so it may fail spectacularly, is, okay, this is nice, but like maybe to make life easier in a visualization, we want to compare things. I want to show the medians for each of these species so we can compare those directly on the plot. So this is a calculated summary statistic to go through. So what we can do is add another geometry. And what I want to add is a vertical line. So I want to put a vertical line for each of these things at the point where that species median occurs. The issue here is like there's not a simple way to put it at the median to do this calculation. So what we want to do is give it a new data set that contains the aesthetic that maps to those vertical points as we go through. And in this context, geom the line, the aesthetic that we actually want here is x-intercept. So that's the x point where we show where this goes. So we need to do two things. I need a new data set that does this, that contains that information where those x-intercepts should be. And then I need to do the aesthetical mapping of x-intercept is equal to the median, or whatever that column is going to be. So I'm getting a little bit ahead of myself. So the nice thing with the geometries is you can use the original data and remap things and do stuff with it, but I can also bring in a brand new data set here. And what will happen is it will pay attention to the other things that I've already set, things like the faceting, the separating by the species, that whole thing. And so what I'm going to do here is put in penguins, group by species and sex. And what I'm going to calculate, summarize, is going to be median is equal to the median of body mass. So if we just look at this by itself, what I'm going to get back, hopefully, is something like this. So I've got species, sex, and median as the columns, because it's important that I have the columns that are being looked for by my existing aesthetic mappings. I have the NA problem as well, so I can do what I did earlier and filter that out. But what I should now have is 6 rows that have each of those numeric values that I want to use. And so I'm going to use each of those values as my x-intercept value to come up with. And so hopefully, if all of this works, we've got a vertical line where each of these occur. Note I'm not getting the color for the species. And the reason for that is because the line uses the color attribute, or color aesthetic, not the fill aesthetic. So what I can do to fix that is just go back up to the beginning and say, do this and color. I didn't like it there, so let's do it here. There we go. So note, the reason I was running into trouble before, if I try to put it in the ggplot, it's getting overwritten in some sense by changing the setting within the density plot. So that's why it wasn't showing when I then try to do it later. So in that case, I can just put the aesthetic in the right place. But now it's not knowing to like map between the two. So the last thing I can do is just turn off that guide. So there we go. So this is some of the power of ggplot, because what I can now do is introduce totally new data sets in there that overlap on top of the existing thing, and it's bringing in that existing information about how I want to separate things, how I want to facet it all, just sort of magically works. I'll leave it there. For exercise 2, if you're really interested in how that's created, like where the colors come from, all the rest, if you actually go to the Palmer Penguins GitHub repo, so this is the main landing page, that's the image I looked at. If you go browse the source code, in this case, the README for this is a markdown file, but it's being generated from an R markdown file. So if you go in there, the code is right there. So that's, again, the power of reproducibility. All the code to generate all the plots that are in the README and everywhere else are right in the document, so you can take it from there. So you can take a look at how it works. That one does some fancier stuff with theme and other kinds of changes, but it should be fairly self-explanatory. OK, I will see you all on Thursday.